Look around at the buildings, the bridges, and even your own body. We naturally assume these structures are rigid and unmoving, but that is an illusion. In reality, every single one of them is an elastic system locked in a constant, invisible battle against physical forces. The rules of this battle were laid out by Isaac Newton. His third law of motion tells us that if a structure is going to resist a load, it has to push back with an equal and opposite force. When a massive stone column is pushing down on its foundation, that force cannot just disappear. To keep the building standing, the earth must push back up onto the column with the exact same amount of force. For any material to generate that upward push, it has to bend. Even if the movement is microscopic, every material and structure deflects when loaded. This deflection is the essential mechanism that enables a structure to function. Ancient engineers intuitively understood this balance. A structure like the Parthenon has stood for millennia by successfully managing the load of its own immense weight through the precise arrangement of its columns and beams. To survive the physical world, every object, from the microscopic fibers in your tendons to massive railway bridges, has to continuously manage two basic actions: the strain of being pulled apart, which is tension, and the pressure of being pushed together, which is compression. Tension is the force of stretching. In biological structures, we see this constantly. When a muscle contracts, it generates a pulling force. But muscle tissue itself is soft and relatively weak, so it needs a mediator to transmit that pull to our bones. That is the job of the tendon. Because a tendon is incredibly strong, it needs only a tiny fraction of a muscle's thickness to handle the same pulling force. This division of labor explains why human hands remain remarkably slender, while the bulky operating muscles stay safely hidden higher up in the limbs. This chart compares strain energy stored per kilogram across materials. Animal tendons safely stores about 2,500 joules per kilogram. Modern spring steel, by contrast, holds only 130. For storing elastic tension, biology vastly outperforms our best metals. Human engineering eventually caught up to this logic. Bridge builders realized they could span much wider rivers by hanging the roadway from above, placing the primary support structures entirely under tension. Early attempts, like the Menai Straits Bridge, relied on chains made from flat wrought iron links. Because the iron was relatively weak, the chains had to be massive, and that required enormous stone towers just to support the weight of the metal itself. The solution was high-tensile steel wire. Instead of heavy iron links, modern suspension cables are woven from hundreds of individual high-strength wires. This reduces the weight and allows bridges to stretch safely over thousands of feet. Tension structures thrive precisely because they are flexible. A continuous, flexible cable automatically adjusts its shape to balance the loads pulling on it. Compression is the opposite problem. It is the force of being pushed together. When pressing down on a slender object, the material rarely crushes. Instead, it becomes unstable and suddenly bows outward. Engineers call this buckling. To prevent buckling without simply piling on heavy, solid material, you have to change the geometry. Pushing the material away from the center into a hollow tube or a cellular grid drastically increases its stiffness while keeping the weight low. One highly efficient method is the structural sandwich. By taking a light cellular grid, like a paper honeycomb, and gluing it between two thin, solid sheets, you create a panel that perfectly resists compressive buckling. Biology has used this exact logic for millions of years. Look at the human skull. It features dense, solid outer layers of bone that sandwich a spongy, cellular internal lattice known as cancellous bone. It provides exactly the rigidity our brains need to survive sudden impacts. We apply that exact same logic at an industrial scale. The designers of the Fourth Railway Bridge used immense hollow steel tubes to carry the massive compressive forces generated by heavy trains crossing the span. Mastering compression is entirely an exercise in geometry. Whether you use honeycombs, hollow tubes, or open-work trusses, the goal is always to arrange the material so it stays rigid under immense pressure. Even with perfect geometry, structures still fail. Often, the culprit is a stress concentration. A tiny defect, like a crack or a hole, causes the invisible flow lines of stress to bunch up tightly together, magnifying the force in one hyper-localized spot. If the material is too brittle, that concentrated stress pays the energy cost to rip the atomic bonds apart. The crack propagates, feeding on the stored elastic energy in the structure, and tears the material apart at the speed of sound. This can happen to metals. During the Second World War, welded steel Liberty ships sailed into the icy waters of the North Atlantic. The cold caused the steel to become dangerously brittle, allowing small cracks to suddenly propagate and break entire vessels in half. This graph shows the stress-strain curves for collagen and elastin, two biological proteins. Nature avoids catastrophic cracks by mixing them into a composite. The stretchy elastin absorbs energy at low strains, while the stiff collagen fibers lock the tissue together as it extends. We mimic this heavily in modern engineering. By embedding strong carbon or glass fibers into a weaker resin matrix, we create synthetic composites. If a microscopic crack forms in the resin, the tough fibers physically block its path, preventing the structure from unzipping. Our physical world is entirely dynamic. From the collagen in your arteries to the steel cables of a suspension bridge, nothing is truly static. Everything around us is constantly stretching, bending, and pushing back against the universe to stay standing.